it says I'm recording it. I hope I'm recording it. I don't see any way to pause the recording. I thought this was going to be more simplistic. Anyway, you can all hear me though, right? Juan, you have joined. You're able to hear me, Juan? All right. And my screen does say solutions and aqueous reactions Friday, November 13th, 2020, right? All right, cool. So we will be, we'll definitely finish up this section today. We're going to finish this section up. Next week, the quiz, I think I have it due on Tuesday, which after today, you definitely should have more than enough information to complete it. All right, let me think. I think I am going to give exam 2 on Friday. So probably same thing as exam 1. You'll have all day to do it, but once you start it, I think I will give you guys a 3-hour limit to complete the whole thing. So there'll be that. What else? That should be it. I think Monday we'll start the next topic, which will be much easier than this last stuff. Actually, once we finish this stuff, things will get a little bit different. We won't be really talking too much about chemical reactions anymore. We'll be talking more about thermochemistry, states of matter, and some other things, because we've hit most of the major topics that I want to talk about involving chemical reactions and such. Any questions on anything thus far? All right, cool. So let's take a brief moment to talk about balancing chemical reactions. So far, all the reactions that I have essentially been giving you have already been balanced for you. You haven't been having to worry about this. But now I would like to involve the idea of balancing reactions. I have this really nice book that has a ton of problems for us to balance. So let us start with this following example. We have the molecule Br2 plus F2 is going to yield BrF3. So this new compound we yielded, I should have you guys immediately notice that on this side of the equation, we have 2 of them and 2 of them, but on this side we have 1 of them and 3 of them, and that can't be correct. We can't have that. So what we need to do is we need to manipulate this equation in such a way that when we're through, that the number of atoms of each of these elements on both sides of the equation, meaning the reactants and the products, are equivalent in number. And the way we do this is by adding a coefficient to the terms. So we will be adding some numerical value there. I want to note that this numerical value should always be a whole number unless I state otherwise. There will be some cases where we can have fractions, but in the cases of this, whole numbers are the only thing that we want. So, what do you guys think that we should do to balance this equation out? Change my pen color to red. So if we put a 2 here, that would mean that we would have 2Br and 6F. So if we put a 3 in front of the F, that means we will have 6F. And that's it. We're balanced. We're good. We do not need to put anything in front of the BR2 because we could put 1 here. But I want to note that 1 is usually signified, so we don't need to put 1 there. We could leave nothing. So we now have balanced this equation. Let's do a few of these. So let's look at, let me see if I can find a difficult one. All right, these are 4-term ones. A little more difficult. So let's get zinc plus HCl is going to yield ZnCl2 plus H2. So we have zinc, we have hydrogen, we have chlorine, and that's it. So currently we have 1 zinc on this side, we have 1 zinc on this side, we have 1 hydrogen on this side, we have 2 hydrogens on this side, we have 1 chlorine on this side, and we have 2 chlorines on this side. So what do you guys think we should do for this one? All right, so 2 in front of the HCl. If we do that, that means we will have 2 hydrogen and 2 chlorine. And, it was just as simple as that. Balanced. Let's see, there has to be a more difficult one in this book. Let's see. All right, this one looks tricky. Let's do C2, F4 plus BRF3 yields C2F6 plus BR2. And so we have carbon, we have fluorine, and we have bromine. So let's see. We have 2 carbon. We have 4, 5, 6, 7 fluorine. We have 1 bromine. Carbon, we have 2. Fluorine, we have 6. Bromine, we have 2. So, how about this one? Okie dokie. So 2 in front of the BRF3. And this will make us 2 BRs, and it will turn our 3 to 6, 7, 8, 9, 10. We have 10 now. Two in front of the C2F4. So this will add 4 more. So this will turn into 14. This carbon will turn into 4. And C2F6. So this will turn us into 4 of these. This will turn us into 12. So it looks like we're still a little short. Let me see if I miscounted. So we have 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're still a little bit off. Let me see. What do I think? So we're probably going to have to play with those C2F4 and C2F6 a little bit. We have the same number with those. The number of, so we're going to definitely have to have the same number of of those two. So these 2 compounds have to have the same number because it's the only source of carbon, meaning that we need the same amount on both sides. So whatever one side's going to be, the other sides are going to be. So 3. So 3 will change this to 6 carbon and 6 carbon. This will change it from 4, 8, 12 13, 14, 15, 16, 17, 18. 18. This will change it to 6, 12, 18, and there we go. We hit it. So it is balanced. So this balancing is mostly just playing with numbers, and I would recommend when you do it to make a chart like I did, like this. This chart really comes in handy, so you could just chart down what you currently have, erase, and then go back and forth. Do you think you would like a few more of these, or do you think this is pretty straightforward at this point? You mean when we break the equation apart specifically? I think we talked about this. Where was it? I think it was this, right? Because this is when we broke the equation apart, where we took the positive and the negative, and we see that when we have a molecule like this, we're going to have the proper number of them, specifically because this calcium is going to have a positive 2 charge, and this hydroxide is going to have a negative 1 charge. So when they're together like this in the formula, they have to be balanced at least to the molecule. Only time they wouldn't be balanced is if you were asked to solve for the product based upon the reactant, and you would have to reorganize. I would recommend going over these notes probably. We're about to go to something very similar to this right now. So you're probably gonna get more examples like that. So I just wanted to briefly touch on balancing because I know I didn't mention it in the beginning. We're going to finish off by talking about oxidation reduction reactions, but specifically, we're going to actually talk about the reactions now. Redox reactions. The last thing we talked about before this was determining the oxidation numbers of elements and compounds. So now we're going to combine this with our knowledge of balancing, and we are going to essentially create and enable change Friday lecture to a Thursday or a Wednesday. Actually, after I think after next week, you guys will be the only ones that I will be teaching. So my schedule will be super flexible. So I could probably change things around. So redox reactions. Let me write this down. So we have zinc plus HCl yields H2 plus ZnCl2. Okie dokie. All right. So this is all I wanted to give you right now. Can you guys tell me the oxidation numbers on these molecules and elements? For instance, zinc. What should the oxidation number for zinc be? Nope. Zinc should not be 2 plus. Zinc should be 0. Because if you go to our oxidation rules, let me see if I have a list of them right here that I can paste. So the oxidation number of an atom in an element is 0. So whenever we see an element that is just an atom like zinc by itself and it does not have a charge, it's just 0. So that is the case for zinc. How about HCl? What should the oxidation state of HCl be? Or rather, instead of the oxidation state of HCl, can you tell me the oxidation state of the hydrogen on the HCl? And then the oxidation state of the chlorine. Yep. So H is +1 and Cl is -1. How about H2? So yes, the total oxidation state is 0. What about the hydrogens in H2? So the hydrogens are each 0 because again we're moving to the we could either look at the elements or let's see the oxidation of a hydrogen in most of its compounds. So these two this rule right here for hydrogen only applies for hydrogen in a compound other than its diatomic state. So when we look at elements, the oxidation number of an element, we are going to include diatomic compounds. So you know the diatomic compounds are H2, F2, Br2, O2, Cl2, I2, and that should be everything. Oh, N2. So these are the diatomic elements. So whenever you see any of these elements, this should be in the it should be in the previous lecture notes. If you see any of these elements, these will always have an oxidation state of 0. So whenever you see any element in its diatomic state, it's going to have a 0 oxidation state. So that's why each of the hydrogens in H2 are 0. Does that make sense? Yeah, we're just it's just basing it on rules. We're just following the rules at this point. How about for zinc in this one? So in this one, zinc is not 0. So we have to look at our rules here. If we look at halogens, the oxidation number of fluorine is -1 always, and each of the other halogens has an oxidation number of -1 in a binary compound, except when the other element is another halogen above it in the periodic table, or the other element is oxygen. So that's a whole bunch of words that are pretty much saying one thing. The halogens will always have an oxidation number of -1, except if there is another element in the compound that is more electronegative than it. So all of these rules are based on electronegativity, and so chlorine, being a halogen, is going to be much more electronegative than zinc. Therefore, chlorine is obviously going to dictate what its oxidation state is going to be. And so chlorine is going to have an oxidation state of -1. And because we have 2 chlorines, there's going to be 2 -1s. And because of those 2 -1s, we're going to have to assign zinc a +2. Make sense? The rules are pretty much very, very similar to how we combine compounds together to create ions. But right here is going to show you the main thing that is going on in these reactions. And you should notice something right now. We see that our hydrogen is going from a +1 charge to a 0. And then what else do we see? We also see that our zinc is going from a 0 to a +2. And this is what is the defining feature of an oxidation reduction reaction. If you see the oxidation states of the elements changing in a reaction, you automatically know that it is an oxidation reduction reaction. And you need to begin asking yourselves a few questions. So the first question is, what is being oxidized? And then, what is the reducing agent? Then you need to ask as well, what is being reduced? And what is the oxidizing agent? So we have 4 things going on. We have a reducing agent, we have an oxidizing agent, and we have something being reduced, and we have something being oxidized. So, what do you think this is when we are going from positive 1 to 0? If you remember those mnemonics I stated, Leo the lion goes grr. So losing electrons is oxidation. So if we're going from positive to 0, that means we're losing. So losing electrons is oxidation, and so we are oxidizing. Whoops, made a mistake here. When, because remember that negatives are electrons, not positives. So when we are going from a positive to a 0, or for instance, from a 0 to a negative, which we might see, we are gaining electrons. So let's see, how should I put this? If the oxidation number goes up, we are losing electrons. If oxidation number goes down, we are gaining electrons. So this is reduced, and this is oxidized. So at this point, I would say there's a lot of terms you have to remember, and that's all there is to it at this point. It's more confusing because there's a bunch of terms here, and the idea behind it isn't that complex. So just if you're having trouble immediately, I would say just try to commit the terms to memory and then look over it again. So what's going on here? We have an oxidation number of +1 going to 0. And so if the oxidation number goes down, we are gaining electrons. And if we are gaining electrons, we are being reduced. So this is reduction. Now, we're going from 0 to +2 here. So if the oxidation number goes up, we are losing electrons, meaning we are being oxidized. Anything not clicking so far? Is it almost making sense? Is it making sense? Yeah, it's just a bunch of terms we have to memorize. And this next thing I'm going to state is going to make things a little more confusing, but it's not really changing anything. If something is being oxidized, it is called the reducing agent. And if something is being reduced, as you probably guessed it, it is called the oxidizing agent. So just another little term for you guys to memorize. So if you are reduced, you are the oxidizing agent. If you are oxidized, you are the reducing agent. Pretty much the opposite thing is doing the other thing to the other thing. So if you are oxidized, you are the reducing agent. If you are reduced, you are the oxidizing agent. Back and forth. So now, based on this, let us do a few problems. This is more or less just the outline of how to figure stuff out. We need to actually define a few things now. So let's pull this down. I want to keep this with us so we're able to refer to it when we need to. So let's go across. So let's look at CH4 plus O2 yields CO2 plus H2O. So can you guys tell me the oxidation numbers for the carbon on CH4? Let me pull the rules up again. I just realized I didn't. So you say it is -4? That is correct. How about for the hydrogens, each of the hydrogens individually? Yep, +1. How about the oxygens? So remember, whenever we see an element in its diatomic state, always 0. How about the carbon in CO2? Yep, +4. And that means the oxygens are -2 each. How about the hydrogen in H2O? So H2O total is 0, but what about the hydrogen by itself? Oh, I see that. You said H2 is 0. So nope, the each one is +1. Yes, so each one is +1. And so if each one is +1, that means the oxygens have to be -2. And so I would have started that one out by saying the oxygen is -2, therefore the hydrogens must be +1 each. So we found the oxidation state of each of the individual elements. Now, can you guys figure out which of these are the oxidizing agents and which of these are the reducing agents, and what's being oxidized and what's being reduced? Question says oxygen from example goes from 0 to -1. Where do you see an oxygen with a -4? I see a carbon with a -4. I see this. Oh, no. These two oxygen right here are going to have 0 each. And these two oxygen here will have a -2 for each one of them. So we do see the oxygen actually going from 0 to -2 in both of these conditions. So we're going to go from here to here and here to here. Yeah, so reducing, so we are going from 0 to -2. And if you go to our rules, if the oxidation number decreases, oxidation means that we are gaining electrons, and so we are being reduced. And so this is reduced. Oxygen here is being reduced. So whenever we have a reduction, we also have to have an oxidation. And so we see that the carbon is going from here to here. And it is going from -4 to +4. And so we are going to be getting an oxidation. So remember, if something is being oxidized, it is the reducing agent. And if something is being reduced, it is the oxidizing agent. So any questions on that one? Let's do a few more, and if you guys can tell me what is being reduced and what is being oxidized for these. So let's say aluminum plus COC. No, it should be little o. Cl2 is going to yield AlCl3 plus CO. Let's do MgO plus H2O yields Mg OH2. Let's do one more down here. Let's do zinc plus chlorine yields ZnCl2. All right. All right. So based upon the oxidation rules here, what's being oxidized and what's being reduced? So one of these two things are being oxidized and one of them are being reduced. You guys have any ideas? Well, what is the oxidation state of aluminum? I'm having a hard time. So remember, rule one. Rule one states that aluminum will be 0 because it's an element by itself. So now we go to CoCl2. So when we get to CoCl2, we look at CO and we don't know the oxidation state of CO. But we know that CoCl2 together has an oxidation state of 0. So I then look at the chlorine. The chlorine will, based on rule number 5, have a -1 unless there is a more electronegative element in the compound than itself. Well, there isn't. Nothing here is more electronegative than chlorine for CoCl2. Therefore, each of the chlorine have to have a -1 charge. And because we know that each of the chlorine have a -1 charge, that means the cobalt has to balance out the chlorine's -1 charge with a +2 charge. So, how about for aluminum and aluminum chloride? What should be the oxidation state of AlCl3? You actually gave the correct answer just previously. It is +3. And the reason it is +3 is because, again, we look at the chlorine. The chlorine is -1 for each of the chlorines, and therefore the aluminum is +3. So how about for this cobalt? What should be the oxidation state of this cobalt? Yep, 0. So based on this information now, yep, because it's a single element by itself, or if it was in a diatomic state, it would have also been a 0. But, so we could look at the aluminum and the cobalt chloride. So of these two elements, which one is being reduced and which one is being oxidized? We see that aluminum is going from 0 to +3, and we see that the cobalt and cobalt chloride is going from +2 to 0. So you're saying aluminum is being reduced. So aluminum is being oxidized, not reduced. Oh, you corrected yourself. So yes, oxidized. And if aluminum is being oxidized, that means that cobalt chloride must be being reduced. And so, remember, if you're being oxidized, you are the reducing agent. And if you are being reduced, you are the oxidizing agent. So let's go to the next one. So how about for this one right here? What do you guys think? What's being oxidized and what's being reduced? Yeah, it is. Well, MgO, I would look at the oxygen first, and the oxygen would decide the Mg. So the oxygen would be -2, and the magnesium would be +2. Same thing here. -2 on the oxygen, and we'd have a +1 for each of the hydrogen. Now with here, we should note that this guy has a negative charge, and there's two of them. And because this has a negative charge, that means this has a +2 charge. And because this has a +2 charge, that means it has an oxidation number equal to its charge. So it has an oxidation number of 2, or +2. And essentially we can -2 and +1. There we are here. Now I want to note that this was a trick question because we see that the Mg is going from 2+ to 2+. We see that the oxygen is going from 2- to 2-, and the hydrogen is going from 1+ to 1+. So no oxidation numbers are changing. So this is not a redox. So remember that if we don't see oxidation numbers changing between the products and reactants, we have no oxidation reduction reaction occurring. Let's do this final example now. How about this one? What do you guys think? What do you think is being oxidized? What do you think is being reduced? Yep, diatomics are 0. And because of that, we know that chlorine is 0. We know that zinc is also 0. zinc is +2. So what's being oxidized and what's being reduced? Zinc is being oxidized and chlorine is being reduced. And remember, whatever's being oxidized is the reducing agent. And whatever is being reduced is the oxidizing agent. All right. So now we're going to talk about the more difficult portion of this. These are called half reactions. So let's say we have the reaction magnesium plus oxygen yields magnesium oxide. So magnesium as an element has an oxidation number of 0. O2 as an element has an oxidation number of 0, and magnesium has an oxidation number of +2, and oxygen has an oxidation number of -2 in magnesium oxide. So the next step that we want to do in this new process we're going to do is we are going to break our reactions into 2 half reactions. And those 2 half reactions are the oxidation half reaction and the reduction half reaction. All right. So for the oxidation half reaction, which of these elements are being oxidized? Magnesium or oxygen? So magnesium is being oxidized, and so this is the half reaction that we will write for magnesium. We will write magnesium is going to turn into magnesium with a +2 charge, and it is going to lose 2 electrons. So this is our first half reaction. And if magnesium is being oxidized, that means oxygen is being reduced. So we have oxygen is going to gain 2 electrons. Actually, I don't want to put oxygen like that. I want to put oxygen by itself. And it is going to form O -2. And so this is how we write our half reactions. We essentially take our oxidation portion, and so if we are oxidizing, losing electrons is oxidation, and so we are going to lose electrons, meaning our electrons are going to be on the product side. Reduction is gaining electrons, and so gaining electrons means the electrons will be on the reactant side. So this is the new thing we have to memorize now. Let's see. I have a bunch of reactions that I want to go through, but I don't know if I want to do them all today or not. Let's do them all today. So our first case is in what's known as neutral conditions. This is the more simplistic form of this type of equation. So the first step we will do is we will be given a reaction, and this is the reaction we are given. We have aluminum plus nickel with a +2 charge is going to yield aluminum with a +3 charge plus nickel. So, can you guys tell me what is being oxidized here and what is being reduced? This is super, super simple because I sort of gave you the charges. Yep, still have to use those rules. And so based on these rules, so you're saying that nickel is being reduced. So nickel is going from an oxidation number of +2 to 0, and aluminum is going from 0 to +3. So we are going to be drawing our two half reactions now. So let me write this out. You said nickel is being reduced. So that means it is gaining electrons. And so we will put nickel I feel you meant to put 3 electrons there, not 2. So it's going to be nickel with its +2 charge plus 2 electrons yields nickel. And then we have aluminum is going to yield aluminum with its +3 charge plus 3 electrons. And so here is where we are at. Any questions so far? Or are we all good at this point? Why is the reduction compared to oxygen? What do you mean? Put the +2 on the reactant side. Yep, because oxidation is losing electrons. So losing. Reduction half reaction, oxygen with the 2 electrons on the left. The reduction half reaction, nickel with the 2 electrons on the left. Oxidation half reaction with the 2 electrons on the right. Oxidation half reaction with the 2 electrons on the right. Am I missing something? Or should I go further up? So if it's negative, the product has a -2. What do you mean by -2? We are essentially balancing the electrons with the charge on it. So we see that we need to go to a -2 charge or oxidation number, and so we need to give it 2 electrons. And we see that we need to go to a +2 oxidation number, so we have to take away 2 electrons. Because we're going from 0 to +2 for magnesium, and so we have to lose 2 electrons, and so we're just pulling them off and throwing them away. And we're going from 0 to -2, so we start at 0, we give it 2 electrons, and then we have -2. So we have the 2 half reactions now, and the 2 half reactions came from the oxidation reaction and the reduction reaction. And we have one final step we need to do to completely balance this equation, because these types of reactions need to be balanced in a more complex way than other reactions. I should have you guys note that in this top reaction, we have 3 electrons. And in this bottom reaction, we have 2 electrons. What we are trying to do is add these 2 equations together so that the electrons in the products and the electrons in the reactants will cancel each other out. So we need the number to be the same. So if we want this top equation to have the proper number of electrons, we need to multiply it by 2. And if we need this equation to have the proper number of electrons, we need to multiply it by 3. That will give us 6 electrons and 6 electrons. So now our electrons are balanced, and the next step is to combine these equations. So let me rewrite this equation out. So we have 2 aluminum yields 2 aluminum plus 6 electrons. And now we will do 3 nickel plus 6 electrons yield 3 nickel. And so at this point, I just rewrote those equations right on top of each other with our lines matching up. And now what we could do is we could cancel out what occurs on both sides of the equation before we combine them. And you'll see 6 electrons, 6 electrons. And now we will recombine. 3 nickel plus 2 aluminum yields 2 aluminum plus 3 nickel. And right here, we have our completed balanced redox equation. So those are the steps that you need to do to solve a redox equation under what is known as neutral conditions. So the neutral conditions are the simplest way to solve this equation. I'm going to do 2 more problems, and then we will be done with this entire section. But these next 2 problems are probably the most complex in this entire section. So the next thing we want to talk about is acidic conditions. Now, in neutral conditions, we only had to deal with our electrons to be balanced on both sides of the equation. Under acidic conditions, we need to take into account H2O and H+. We have the ability to add either H2O or H+ to either side of our equation to help us balance it. That is the purpose of these two compounds when we talk about acidic conditions. So let's start this example. So let's say we have zinc, and zinc is going to react with BrO3 minus to form zinc plus 2, and then it is going to generate bromine with a -1 charge. So based on this equation, what do you guys think is going to be oxidized and what is being reduced? So this is correct. So we have zinc generating the zinc plus 2 electrons. And we have BrO3 plus, let's see, 1 electron. Let me pull this back a little bit. Oh, no, it's not 1 electron. That is 6 electrons. Is it 6? 3, 6, 2, 4, 6. Yes, 6 electrons. Yields Br minus. So this one's a little bit more tricky. It's because we have an overall charge here of -1. And so this means that this Br has a oxidation state of 6. And then it's going to an oxidation state of -1. So now remember, when we are doing these types of equations, we need to look specifically at how many electrons we have in each of them. So in the top equation, we have 2 electrons, and in the bottom equation, we have 6 electrons. So we obviously need to do something here. Well, we could actually multiply the entire top equation by 3. And if we multiply the top equation by 3, we will see that we end up with 6 electrons on the top. But I don't know if you noticed something, but there's a bit of a problem here. What happened to the oxygen? So this is why this type of equation is considered under acidic conditions. We have to do something to add that oxygen. And how are we going to do that thing to add that oxygen? Well, we're going to add water. So now we have that oxygen added. But how many oxygens do we need specifically? Well, BrO3 has 3 oxygens, and so we need to add 3 H2Os. So now we have a total of 6 oxygen here. But now we have another problem, and that problem is, well, we have hydrogen. So we need to do something to deal with the hydrogen now. So as you see, because we could add hydrogen, let's actually add some hydrogen to the left side of this equation. So we just put some hydrogen on the left side of this equation, and let's see if we are balanced at this point. And we have 6 hydrogen on the left. We have 6 hydrogen on the right. We have a Br on the left, a Br on the right. We have 3 oxygen on the left. We have 3 oxygen on the right. And here is our 6 electrons that are being consumed. This was a little bit more involved, but are there any questions on how I essentially pulled this together here? All right. I don't think we actually might. Yeah, let me just delete this. We shouldn't need this anymore. So now that we are balanced, we could combine our equations. But wait, let me actually do this multiplication step first. So we're going to get 3 zinc yields 3 zinc with a +2 charge plus 6 electrons. We have 6 hydrogens with a positive charge plus BrO3 with a negative charge plus 6 electrons, negative charge, our reactant arrow, Br -1 plus 3 H2O. And then draw our line. And let's cancel out what occurs on both sides of this equation. Cancel out those 6 electrons there, 6 electrons there, and now we can combine our equation together. We will get BrO3 negative charge plus 6 hydrogen positive charge plus 3 zinc yields 3 zinc with a +2 charge plus bromine with a negative charge plus 3 H2O. So this was a bit more involved than the previous example, but it's the same general concept. The only addition we're doing is we are adding H2O and we are adding H to balance the equation slightly further. Are there any questions on this problem? So the final example I want to go through today is on what is known as basic conditions, and this is the most difficult of them to solve. All right, so in acidic conditions, remember, we were able to add hydrogen and H2O. In basic conditions, we are going to add H2O and OH. Now, I want to make one more thing clear. When we balance an equation under basic conditions, we should always balance it under acidic conditions first. because balancing it directly under basic conditions is more difficult because it's in acidic conditions with H2O and H. We only have to deal with H on one side of the equation. With basic conditions, we have to deal with an O and an H together, which makes balancing more tedious. So instead, if we balance under acidic conditions and then convert to basic conditions, it's a lot more easy. So we have aluminum plus ClO4 yields aluminum hydroxide plus Cl minus. So from this equation, what is being oxidized and what is being reduced? Yep, aluminum is being oxidized. So aluminum is generating aluminum hydroxide. The minus charge plus 3 electrons. And why is it 3 electrons? Well, we're going from a oxidation number of 0 to an oxidation number of 3. And you see why it's going to these numbers, right? And we are going from ClO4 plus let's see, we are going how many electrons? So 4, this is 8. So this is an oxidation number of 8. And this chlorine is going to an oxidation number of 1. So because we are going from 8 to 7, minus, this is 8, this is -1, and so that's how we do it. Oh, whoops. It should be 9. So the H2O and the OH, we have our half reactions. We now need to balance them further. So we need to add hydrogen and H2O first. So I want to make a distinction somewhere here. Let's put it right here. 1 OH yields, or 1 OH plus 1 H equals H2O. So when we add H and OH together, we get H2O. So that is what I want you guys to simply take into account right here. So what I'm going to do is on this equation right here, I am going to add OH. And specifically, I'm going to add 4OH. Because we needed to add the OH to balance this OH. No way around that. I had to do it like such. So we now have 1 aluminum, 4OH, 4OH, and we are balanced on this side, right? Doesn't seem like anything's wrong here. Any disagreements on this so far? For that first equation? What do you mean changing the oxygen? Yep. So that's the first half reaction, and now we're going to deal with the second half reaction. And so this second half reaction, I am going to balance in a different way. I am going to balance it under acidic conditions first, and then I am going to balance it under basic conditions. And because, remember, we see this ClO4, but we have no oxygen on the right side, we need to balance the right side of the equation a little bit. So in order to balance this ClO4, I'm going to add 4H2O to this side of the equation. And in order to cancel this 4H2O, I am going to add 8 hydrogen to this side of the equation. All right. Because now we have 8 hydrogen on the right, 8 hydrogen on the left, 4 oxygen on the right, and 4 oxygen on the left. So now we're balanced under basic or acidic conditions. We need to convert this to basic conditions. So what I'm going to now do is I'm going to add a hydroxide equivalent to the number of hydrogens. The reason I am doing this is because, do you remember up here I show that if we have a hydroxide and we have a hydrogen, we have water. So if we add a hydroxide to a hydrogen, we make a water. But at the same time, we are able to add hydroxide to the right side of the equation and keep things basic. So this is why I said to balance things under acidic conditions first. So this is what we're going to get. We're going to get 8 H2O plus ClO4. I believe that should be a minus, right? No, it's not. ClO4, yes, that should be a minus. This changes things. Give me 1 second. So if this whole thing is all right. There should be another minus right there. Let's see, did I miss any? Okay. All right. So we have these guys. plus, there should not be two pluses, are 9 electrons. Yields Cl minus plus 4H2O plus OH minus. That should be everything. Here's our H2O, ClO4, our 9 electrons, chlorine, 4H2O, hydroxide. Awesome. So now, let's see. All right, we could do another part of this. We can simplify this slightly further. I want to note that we see that H2O is occurring on both sides of this equation. So we cancel out 4 to bring it to 4. We could rewrite this to 4H2O plus ClO4 minus plus 9 electrons yields chlorine plus OH minus. All right. This should be 8. So this is 8, 8, 8. Because the overall charge on the ClO4 is a -1. We have a let's see, 2, 4, 6, 8. We know that we have a -8 charge on the 4 oxygen, and because we have the overall charge of a -1, we know that the chlorine should be a +7. I want to make that correction. Do you guys see that correction that of the mistake I made? I just want that to be noted. And because of that mistake, instead of having 9 electrons, we only have 8 electrons. So from going from 7 to -1, we only have 8 electrons. So instead of going from 8 to -1, we're going from 7 to -1. So we have 8 electrons and 8 electrons. All right. I believe that corrects that one mistake I made. All right. It looks like we're good here. Okay. So we have our bottom equation. It looks like it is all worked out. We have everything balanced. So this is our half reaction number 1. And our half reaction number 2 is right here. Let me just carry it down. It was the simple one. We didn't need to really do anything to that one. So let me put it right there. So after we played with both half reactions, we have these two. And we are almost done. Almost. Notice how we have 8 electrons on this one, and we have 3 electrons on this one. We need to multiply these equations by something in order to essentially fix that. Oops, I made another mistake. Wow, I made a bunch of mistakes. Because I remember I added 8 hydroxide to this side. I should have added 8 to this side. 8. 8. There we go. That fixes that. Okay, awesome. Okay, we're all good now. We should be all good. So what we need to do is we need to multiply these equations by something to make our electron count equal the same. We have 8 electrons here, and we have 3 electrons here. And the only way to essentially knock those out is by essentially multiplying by 3 here and 8 here. When we do that, we will get the following equation, which gives us, let's see, 12 H2O plus 3ClO4 minus plus 8, 16, 24 electrons yields 3 chlorine plus 8, 16, 24, 24 hydroxide. We're going to now multiply the bottom equation. 8, 16, 24, 32. So we have 32 hydroxide plus 8 aluminum yields 8 aluminum hydroxide plus 24 electrons. So you guys still with me so far? Everything straightforward so far, besides my few mistakes? We are on the home stretch right here. This is the last part. Yep, we just need to balance out the electrons. We need the electrons on both of these equations to equal the same number. So 24 and 24. So once we get the electrons, we are able to cancel them out. We actually might be able to cancel out a little bit more than just the electrons with this. As you see, we have 24 hydroxide over here. And we have 32 over here, which means that we are left with only 8. And let me make sure everything else cancels. I think we might be able to cancel out something else. Let's see. I thought I got rid of the H2O. H2O. Nope, we're all good. Say that one more time. Oh wait, no, never mind. You didn't say that. Let me read that. That is right. You can get rid of the O and the O. Yes, that looks like all that we could get rid of. So let's leave us with 12 H2 plus 8 hydroxide plus 8 aluminum plus 3ClO4 minus yields 3Cl. Let's see what else we have. Plus 8 C or 8 Al OH 4 minus. I'll make sure I got everything here. All right, it looks like I got everything. So this should be the completed balance equation once we take care of everything. This was a very, very long process, I understand. But this is probably the most exhaustive process that you will do for an equation like this. So this is really like hitting everything. Are there any questions specifically on this? All right, so that will conclude everything that I want to talk about relating to aqueous reactions and balancing equations and aqueous like dilutions and molarity and everything. That will essentially conclude this entire unit. So I think exam next week on Friday. I have the quiz due on Tuesday. If there are no other questions, that's pretty much all I want to talk about today. So I think we'll do a lecture on Monday, but no lecture on Friday.